Hello, welcome to your subject Theory 2 or Theory of Structures 2. Okay, so we'll start with your Module 1, Introduction of Theory of Structures 2. Okay, so under Module 1, we will have here your Unit 1. Okay, Introduction to Statically Indeterminate Structures. Okay, by the way, I am Engineer Angloan. Okay, I will be your instructor for this subject. Okay, so in your theory 1, that is the analysis of determinate structures. If you say determinate structures, those structures can be solved by the three equations of statics: the summation of forces x, forces y, and then summation of moments. Isn't it? That those are the three equations of statics, or we call that one the equations of equilibrium. So that is your theory 1. Now we will proceed with indeterminate structures. That is your theory 2. So in your theory 1, you discuss how to solve your reactions, your member forces for trusses, and then of course drawing your shear and moment diagrams for frames and beams, and also you discuss of deflections. Okay, so that is your theory 1. Now this is your theory 2. So in this unit, okay, under unit 1, this is your desired learning outcomes. First is for us to understand what is indeterminate structure, and then to determine the indeterminacy of structure, what is that indeterminacy, and then to check stability, instability of structure. Okay. So, okay, let's try to understand what is indeterminate structure. So it says there, a system is said to be indeterminate if the support reactions and the internal forces cannot be determined using statics alone, or that statics is the equation of equilibrium. That is what I'm saying a while ago. If your structure system cannot be analyzed by merely equations of equilibrium, then you need to use there any other types of equation, then that is now indeterminate structures. So why is that? Okay, why is that the case that we cannot just solve that one using equations of equilibrium? Because okay, indeterminate structures consist of more supports and or it could be only more members, or it could be both. Okay, so as you can see here that the indeterminate structures consist of more members and or, that is the emphasis there, and or. So it could be that the member will be more, okay, than what is required, or the support is more than what is required. So you need minimum of three supports, I mean three forces in your supports, so that you can solve, or a maximum of three forces in your support, so that you can solve using equations of statics. But if that is now more than, then you cannot just use your equations of equilibrium. Okay, so the excess members or supports are called redundant. That is how we call the excess from the determinate structure. These redundant forces can be solved using the compatibility equations, okay, in addition to the equations of statics. So as I'm saying, isn't it, in algebra, the number of unknowns should be the number of available equations for you to solve the unknowns. Let's say you have there five supports, so unknown forces of supports, but you only have there three equations of equilibrium, then you need two more for you to solve these five equations, five unknowns of the support. So again, that is the law of your algebra, and you cannot do something about that. Okay, and then the question there is, what is that compatibility equation? So where will we get that compatibility equation? Isn't it that in your theory 1 you discuss also the deformations of your beams and frames and trusses? These are the moment area method, conjugate beam, and so on and so forth. There are a lot actually, but you can stick to the method that you are comfortable with. So if you are trying now to make use or to create a relationship based on the deflections and rotations, or based on the deformations, we call this one the compatibility equations. So if you will try to derive an equation from those deformation, we call that one the compatibility equations. So how is that? For example, okay, we know that in isn't it, for example, this is your beam. We know that the deflection within the beam at exactly where the support is is positioned, the deflection there, or if you say deflection, that is the displacement vertically, okay, of that beam, the deformation there or the deflection there is zero. Why? Because that is where the support is applied. So that will never deflect unless, of course, your support is unstable. So making use of that idea that that support will not deflect, you can actually create an equation out from that, out from deflection or out from rotations. Okay, so that is how we will end up with the additional equation for us to solve the additional unknown, the redundance. So compatibility equations. So that is indeterminate structure. So what is the advantage of this? Okay, actually, if you will try to look at the structures, a lot of structures, example, building. If you will try to look at the buildings, if you will try to consider one beam of a building, of course, that is the common. Okay, the common scenario is that you can see that the beam is connected to the column, or in the column is of course expected to be fixed, and the other side is also connected to another column. So that is the actual scenario. Fix on the other side and fix on the other side. So how many reactions are there? Three, and on the other side are three. So total of six reactions. So you cannot just solve that by merely equilibrium. So you really need to know how to solve the indeterminate structure, because most of the time, again, that is the common. Okay, that is the common type of structure that we have on the actual indeterminate structures. So why is it? Okay, what is the advantage of that indeterminate structure? If we can make use of determinate, and that will be simpler to solve, why use indeterminate structure, isn't it? Okay, so first and foremost is that the first or the most important advantage of indeterminate structures, that the stresses on the members will be smaller. Okay, for example, okay, in this one, in this beam, your support here is a pin and a roller. So that is actually determinate. There are three equations that can solve the three unknowns, the three forces of the reaction, isn't it? So we can just solve that one. But if you will try to load that one, let's say I will load that one, that will deflect this way. But if you will try to consider an actual scenario of beam wherein you have here a column and a column, or that is fixed or fixed, the both ends are fixed, then of course you have a lot there of, there are six reactions there, isn't it? But you cannot just use their equations of equilibrium. But what is the advantage of this? If that is fixed and if that is fixed, of course, the deflection is smaller, because again, there will be a resistance of moment here and resistance of moment for that to control the deflection of your beam. Okay, so the smaller the deflection, of course, the lesser the stress on your members. Or one other explanation or one other meaning of indeterminate is that not just on the support, isn't it? Let's say we are talking about trusses. If you are going now to create a truss and you are going to apply a lot of bracing, the more bracing, the more secure your truss is. Okay? Why? Because there are a lot of members that will be carrying the applied load on your truss. So the more the members, the lesser the forces, because it will be distributed. So that is the advantage of your indeterminate structure, which is actually the case on actual construction. There are only seldom that uses your determinate structure. Okay, so we have here your greater. The advantage of that is greater stiffness. That's like what I'm saying here. If we are talking about stiffness, that is how firm. Okay, uh, the capacity of the member to resist deformation, that is stiffness. Okay, that is how we call it, stiffness. So actually, that if you are just looking at this figure, that is talking about the deformation. Okay, an indeterminate structure show less deformation than determinate. Just look at this example: a beam with no moment to resist, that will give us a bigger deflection compared to a beam that is actually secured by fix both ends. Then that will just give us a small deflection. Okay, so that is another advantage of your indeterminate structure from determinate. And what else? Redundancies. This is what I'm saying a while ago. This is related with your smaller stresses. Okay, so if you have more, for example, indeterminate with more members, okay, you have there a sudden apply a force or an impact force that will be applied on the structure. For example, you have a building, there will be a sudden earthquake, so there will be a lateral force that will shake your building. The one that will receive that one is the members, of course. That is the one that we are designing on buildings, not the walls. So these are the members of the building that will resist the movement or the force of the earthquake. So, by the sudden impact of that earthquake, there will be a sudden impact on the stresses or stresses on the members. And if that is just determinate, even if that is well designed, if that is not sufficient enough, that will break. But the good thing, if there is a redundancy or there are a lot of members, okay, let's say that there are a lot of members. That is redundancy means general, okay. So there are a lot of members. Let's say that there is an extra member that will carry even if the other member will break, then that is the good thing. The structure will not collapse. Even one of the member will snap. Okay? If the other member is designed to carry the structure without the presence of the other member. Okay, so again, that is the good thing of indeterminate structure. If the other member snaps and there is another redundant member there, it will it will carry the load carried by the previous member. So that is redundancy. So those are the advantages. Those are the important things that we need to know about indeterminate structure out from your determinate. But actually, again, determinate is also applicable on actual. For example, for most of the time that we are using a determinate is that on bridges, okay. So what happens there is that if your member of the bridge of your bridge is what you call this one, if the beam of the bridge is just laid on top, okay, on top of the piers, then actually that is not a fix. That could just be actually a ruler or it could just be a hinge. So that is an example of determinate structure. So it is also applicable on actual construction. But for most of the frames, just like frames, that is for indeterminate, most of the time, indeterminate structures, frames and beams. Okay, so we will try now to talk about indeterminacy. How do we know the degree of indeterminacy? How indeterminate your structure is? We have what we call as the external and internal indeterminacy. If we are talking about external, we are talking about the indeterminacy of the supports. Okay, it is the global indeterminacy or the external. So if we say external indeterminacy of a structure, okay, how do you know that one? So you need that for that to be indeterminate, okay, for that to be indeterminate, the support should be more than the equations of equilibrium. So if your reaction forces is more than 3, then automatically that is indeterminate. However, there are some cases wherein, let's say there are internal conditions. For example, there is an internal, look at this beam here that we are frame here. We have here your internal ruler, okay? That is a given condition, isn't it? Wherein you can cut your structure here. Even if that is not a truss, you can do that one. You can separate, analyze this side, and then analyze that side. That is additional condition, equation of condition, which is actually another added equation to the equations of equilibrium. So even if it is not just three reaction, even if there is 4 or 5, if there are other additional equations of condition, you can solve that one, or you can consider that one as determinate. So in indeterminacy, in degree of indeterminacy, we will consider those equations of conditions. Okay. So the excess in your reactions, so if you say reactions, it could be coming from support or it could be the internal reaction. So that is your internal indeterminacy. Okay, so let's just focus first on your external, or we are talking here of your supports. So the reaction of your supports, here is the R. Subtract how many equations do we have? Of course, that 3 there, that is the equations of your equilibrium, plus whatever additional equations of condition that is added in your system. So if you try to look here, okay, so I will first explain what are these. I sub E, that is your external degree of indeterminacy. External, so we are talking about supports here. So if that I sub E, or simply I, is less than 0, that is unstable. It means that your support is lesser is lesser than what is required, of course your structure will not be stable. I will explain that one. That will be in your instability. That will be our topic later. However, if that will be exactly zero because the reaction is exactly equal to the equations that we can use, then that is determinate, isn't it? Yes. So I will be zero, or the degree of indeterminacy is zero. But once your reaction is more than the equations available, you will have there more than zero, or a positive number. Okay, and that is now your indeterminate. So you can decide if that is determinate or indeterminate or even unstable by merely looking at the equations or the external degree of indeterminacy. Okay, so your R there is the support. Okay, so that's what I'm saying, and then the E sub C is the equations of condition. So let's talk about that equation of condition. There are a lot of ways to make your structure determinate by adding internal hinge, and then or hinge or internal pin, or by adding internal ruler. So in your figure I gave here the two. You have here an internal ruler. That is not an external support, because that is just a support connecting the members. It is not a support wherein it will not receive the carried force by the member. For example, if you try to look at this is a support, a pin support. Why? Because it is carrying whatever is carried by the members. But this one, this ruler here is just to transfer whatever is carried in this left side to the right side, or vice versa. So that is just a condition. That is not actually an external support. That is internal, or we call that one the equations of condition. And we have here also hinges, or we call that one the internal pin. Okay, so in your, what is the number of that E sub C if you are having a hinge? Okay, hinge, it depends actually, or internal pin, we call that one internal pin. It depends actually on how many members is connected to that internal pin or hinge. So how many equations are we going to add out from this hinge is n minus 1. N is the number, okay? N is the number of members connected. So in this case, our n here is 3, so our E sub C here is 2. Okay, and then for ruler or internal ruler, that is twice the quantity n minus 1. So again, n is the number of members connected to your internal ruler. But most of the time, if you are talking about 2D frames, then that is most of the time 2 members only. But there are some cases wherein there is a third, a fourth, or more than 2 members. Okay, so since this is in this case, you have there only 2 members, so n there is 2, so 2 minus 1 is 1. Multiply that always to 2 if you are having ruler. Okay, so in this case, that is 2 minus 1, so that is 1 times 2, so your E sub C here is 2. And then your E sub C here is 2. So, all in all, our added equation to your equilibrium is 2 plus 2, which is 4. So, a total equation that is present in your system is 3 plus 4, which will be 7. Okay? Now, if we will try to compute the external degree of indeterminacy, all we need to do is find out first the reaction. This is a fixed support, so there are 3, the moment, the vertical, and the horizontal. Do not consider those as a support again, guys, okay? This is a support, this is a hinge, so there are 2, a horizontal and vertical. A hinge, so 2, a hinge, and that is also 2. So 2, 4, 6, 8, 9. So 9 total reactions. So that is your R in your formula. However, your E sub C there is again 4. Substitute there plus 3, so that will be 7. So 9 minus 7 is 2. So there are 2 redundants. Support external redundant or support redundants. Okay, so you cannot just solve that one using summations of forces or by merely statics, even if there are additional equations of condition. Okay, so that is external indeterminacy. We are talking about the support out externally of the structure. That is general. By the way, however, in trusses, okay, you might be saying that in trusses, isn't it that truss? That's how we define truss. Truss is a structure that is transferring actually a load in a way that your connection is all considered to be pin. isn't it? Or hinge. Do not consider those as additional. Do not consider those as additional condition because in trusses, that is known to be that way. So in trusses, all you need to do is forget about that additional condition. Okay, unless there is an external or internal ruler. But again, you can forget about that external or equations of condition in getting the external indeterminacy of a truss. So all you need to do is get the number of reactions, subtract the three equations of equilibrium, then that is the external indeterminacy of truss. For frames and beams, of course, consider your E sub C. So internal indeterminacy of frames. How about that internal? So as I'm saying, if we say internal, we are talking here, there are reactions. These are the member reaction. These are the member forces. Okay? So those are the force applied by each member. So how do you know that? How can we say that this is indeterminate internally? Because even if there is just enough reaction, let's say there are only three reactions, you can solve that using statics. If your members are too many, or for example in a truss there are a lot of bracings, then you cannot just solve that one. You cannot just solve that one by summations of this equilibrium. Then that is internally indeterminate also. Okay, it could happen because even if your support is determinate. So there is an internal indeterminacy. Okay, for frames, this is the formula. So let's just change that one to sub I. It means internally. A while ago that is sub E. That is externally. So 3m plus r. So we are talking here of the reactions. Okay, reaction minus the equation always for you to get the degree of indeterminacy. So this 3m plus r, this is actually reaction, wherein r is the reaction externally and the m is the reaction member reactions, or that is the member forces or the number of members that will react, that will support the load. Okay, so this 3 plus m is actually the reaction, and that quantity that is enclosed is your equation. Okay, so that is 3 times j, wherein j is the joints and m is the members, r is the support reaction, of course, E sub c there is the equations of condition. Again, so we have the equation of condition that will help to solve the member forces also. So how do you know that that is internally indeterminate is make use of this formula again. Okay, so this is the supports and these are the equations. So M, how many members? For example, the same here. Okay, this is externally indeterminate to the second degree since that is 2. Okay, how about internally? Let's try to calculate using this formula. Okay, so I sub I. Okay, 3 times M, our member is 1, 2. Okay, by the way, how do you know that that is a member? We will try to cut your, even if that is a continuous, we will try to cut the member and count the member by supports. And if there's a joint, we will consider that to be a member. So for example here, from this internal ruler to that hinge, even if that is continuous, that is considered to be one member. Okay, so how many members? 1. This green, that is the green numbers here. 1, 2, 3, 4, and 5. So there are 5 members. And then your reaction, of course, we solved that one a while ago to be 9, and so with the equations of condition, that is 4. That is a while ago, R and E sub C. What is the joint? Okay, of course, we will consider the joints if the equation condition, and the supports will be considered as joints. Okay, so this one, even if there is no hinge here, that will be considered as joint. So 1, this is the red color, 1, 2, 3, 4, 5, and 6. There are 6 joints. So substitute that one to your formula. R is 9, M is 5, J is 6 times 3, okay? 4 is your E sub C. So calculate that one. Internal degree of indeterminacy is 2. So again, it is indeterminate to the second degree internally. So it so happened that your external indeterminacy and internal indeterminacy is the same, but that will not always be the case. Because maybe there will be more members, okay, or there will be more supports. So that depends, but in this case, it so happened only that it is the same. How about, okay, so as you can see, this is general for structure. So it could be a truss or frame. Okay, but if that is trust, you can forget about that E sub C in your external indeterminacy. This is only for frames. Okay. How about if that is your truss? So in trusses, it will still be coming from that equation, this one. However, in trusses, since we will not consider the joints of those to be equations of condition, since that is to be given, that is given on trusses, isn't it? That should be hinge or pin. Then you can reduce actually the equation here, since how many pin are there in one member? There are two. Okay, in one member there are two. So there are two hinge. So multiply that number of member to 2, since that is the total number of E sub C. But isn't it that subtract, since in each member we will only be using one n for the equation. So that is the minus 1 for each and every member or each and every joint. So we will just substitute that one by minus j. So the total E sub C in the whole truss is 2m minus j. 2m minus j. Wherein if I will substitute that here in your E sub C, you will now simplify actually that one to be, okay, 2m, that will go out as minus. So 3m minus 2m, it will just become m. R will be remained as r. 3j minus j will be 2j, it will go out as negative 2j. So we will simplify the equation to be m plus r minus 2j. So that is for trusses. Okay? So that is the internal indeterminacy of trusses. That is how we will know if it is indeterminate internally, if there are more braces. Okay? So the same, by the way, the same, if your internal indeterminacy is less than 0, less than what is required, that is still unstable internally. Okay, I will explain later on what is internal and external instability. If that is equal to 0, of course, it is determinate. It can be solved by merely statics. If that is more than 0, or that there will now be a degree of indeterminacy, it is indeterminate, internally or externally. Okay, so for trusses, okay, let's try to have this. So again, these are your definitions. So M is member, R is the reaction, support reaction, J is your joints. So if you try to look at this, how many reactions do we have? This is a ruler and a pin. So 2, 1, and 1. So that is R is 4. How many members? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9. That is the green number. And then joint, how 1, 2, 3, 4, 5, 6. So there are 6 joints. So substitute that one, you will end up with I sub I, or internal indeterminacy of the truss, to be 1, or that is internally indeterminate to the first degree. Okay, first degree. So that is indeterminacy. So that we will know if it is indeterminate or determinate. So that you can know if you can solve that one by merely statics, or you need the compatibility equations. Okay, so instability. Okay, we will now move on what is unstable. So we will discuss here what happens if your degree of indeterminacy or your support is less than what is required. If your external support or internal support is less than what is required. So instability. How can we say that that is unstable? So a structure is said to be stable, okay, if it can resist applied loads without moving or collapsing. Okay, that is how we will know if your structure is stable. But once the structure will receive the loading and that will now be moving, that is unstable, or that will collapse, that will fall, then that is unstable, or that is considered as failure. If you are considering the strength of the member, that is failure. But if you are talking about the arrangement of the frame or the trusses, that is collapse, or that is what we will be talking about later on, which is collapse mechanism. Okay, I'll explain that one later on. Okay, so again, structure is said to be stable if it can resist applied loads without moving or collapsing internally. Okay, without collapsing internally, assuming that all members are sufficient to carry the respective stresses. Okay, so even if your members are designed correctly to carry whatever the load is applied, if the arrangement of that members is not also coinciding with the application of the load, or will not be with the flow of the load, then that will collapse even if those members are strong, okay, internally. Okay, so let's try to discuss what are these causes of instability of structure. Okay, so first is insufficient reaction. So this is in this figure. Consider this figure. Let's say this is your frame. That could be frame or truss. Okay, if this is your frame and you are going to apply a force there, force F, let's just say force F, then you are supporting that one externally by a pin. And what is the reaction of a pin? It will only hold that one horizontally and vertically. It will never hold that one against rotation. So as you can see, look at this. That is pressing your structure going down. Of course, that will tilt. Okay, that will rotate. And the support here below cannot offer a resistance of moment. Only a horizontal and vertical resistance. So this is unstable because that will rotate or that will tilt. Okay, so we can call that one as the unstable, insufficient reaction. Insufficient reaction. What else? Parallel reactions. Look at this second figure here. Okay, you have this truss. Let's say this is your truss, and you are going to support that one by two ruler. Yes, that will stand if you will try to apply a vertical load. But once you will apply here a force that is perpendicular to the parallel reactions, okay, parallel reactions, there is no resistance against that one. So if you will try to summate forces horizontally, there is no reaction that will counteract the effect of that horizontal force. So of course, that is just like a car that will now move to the right. Okay, so that is unstable, and there is no structure to be designed as unstable this way. You cannot design a building that is moving horizontally. Okay, you need to have restriction. So that is also considered unstable. See, there is concurrent forces or concurrent reactions. Look at this one, this third figure here below. If you are, let's say you have here a beam and you are going to support it this way, how many reactions do we have? A ruler, ruler, and ruler. So there are three rulers. So yes, there are three reactions. So isn't it that is enough supposedly? Because three equations is enough. I mean three reactions. However, the what we call this one, the orientation of the reactions is will make it unstable because they will meet. We call this one the concurrent. They will the direction of action of the reaction meet together. So look at this. It's okay if I will apply again. If I will apply here a vertical, nothing carry since that will be symmetrical. But if I will apply an inclined or horizontal there, this is a ruler, this is a ruler, this is a ruler. That will also tilt that way. So this is unstable. So again, parallel reactions, insufficient reactions, and concurrent reactions are prohibited for your structure to be stable. And this is now we are talking. These are external instability. There will be a movement externally. Okay, but if we will now talking of if we are now talking about the reaction of the members, okay, the forces applied by the members to resist the force. Let's talk about this internal collapse mechanism. That is what I'm saying, collapse mechanism. Okay, so if you'll try to consider here, okay, you have this one. This could be a truss since that is connected by pins or hinges. So if you'll try to look externally on the supports, there is a resistance. There is a resistance with respect to horizontal, so that will not move. There is a resistance with respect to vertical, it will not move. But again, if I will apply there, so just like this one, however, this is insufficient because in the first place that is only two reactions, but here there are three. So you might be saying that will be enough, but you have to apply this force F. Since there is no bracing that will hold the diagonal bracing that will hold or that will receive the force horizontally, okay, in the member, of course that will not move horizontally as a structure, as a whole, because again that is a pin, so that will not move. But that will collapse this way because again there is no bracing. So that is the use of your bracing. And in trusses, for that to be a well-designed truss, or we call it a truss because in truss, the formations of your members is a triangle, okay, so that it will resist vertical, horizontal, or even inclined. But in this one, this is just a square truss, if that is a truss. So, of course, if you will apply this force F, that will collapse this way, even if it will not move as a whole structure. So that is collapse mechanism. The instability is internal, is within the members, the arrangement, orientation of the members, not in just the supports. Okay. So again, instability will come from the orientation of the reaction, the number of reaction, and of course the orientation of the members for your structure to be stable. So as an engineer, later on, if you will design, this is what you need to understand. This should be a what to call this one common sense to you. If you are designing a structure, you need to consider the mechanism, or you need to consider how the force is applied on the structure that you are designing, so that you will know how to design the shape of the frames of the truss to resist that kind of loading. Okay, so that is instability of structure. So that is for your unit 1. So what are the important concepts here is that indeterminate structure consists of more members and more supports than what can be solved using statics alone. So that is how we will classify indeterminate with your determinate structure. And instability of a structure is due to insufficiency of supports. Okay, that is what I'm saying a while ago. If you have insufficient support that can move laterally or that will tilt. Okay, orientation of supports. So again, there should be no concurrent reactions, or there should no be parallel reactions. Even if there's a parallel, as long as there is another reaction against or perpendicular to that. And then of course, absence of lateral bracing, or that is orientation of your members so that it will not collapse. But of course, you'll try to look here. If that is truss, that will happen to truss, since your truss is designed to be having its joint as pin or hinge. So isn't it? Hinge, there is no resistance for movement. But if this is actually a frame, if it's a frame, this is a rigid body, then even if there's no bracing here, just like on buildings, isn't it? That is that is the actual scenario on buildings. There is no post that is inclined connecting it to the beams. No, because that is designed as a frame. So a frame will resist a moment. So even if there is no lateral bracing here, or there is this is the orientation of your members, if that will resist is designed to resist a moment, then that will stand. Since this we assume that this is a truss, so that is pin connected, so that will collapse that way. Okay. So these are the important concepts of your unit 1. Okay, of your introduction. Indeterminate structure, determinacy, and instability. Let's proceed with your. So if you have any question, you can comment below, but we will continue with your unit 2. Okay, unit 2 under module 1, still on your introduction. So why is it that it is in your introduction? Because we are just trying to recall some of your deformations of your structures. Okay, let's try to recall, since that is discussed in your theory 1. How we will compute, since again, as I'm saying, if your equations of equilibrium is not enough, you need to have other equations which will be coming from the deformations. So we call that one the compatibility equation. So we need to know, or let's try to recall, since we will be using later on the deformations, your deflection or your deflection or your what do we call this one, rotation or slope. Okay. So let's proceed. So in this unit, we are going to recall the moment area method of determining deformations, and then we are going to recall conjugate beam method of determining deformations. These are actually the commonly used or generally used method of analyzing deformations of beams, deflection, and rotation. Actually, there are a lot. We have the unit load, you have the virtual, and then you have the, if you are dealing with equations, if you are fond of equations, you have the double integration. The double integration. Yes, there are a lot of methods if you'll try to recall your theory 1 or mechanics. Let's just recall these two. Okay, so moment area method. So isn't it in moment area method, you have two theorems, your theorem 1, moment area theorem 1, and then moment area theorem 2. So the first theorem of moment area method is that the change in slope between the tangent drawn from 2 points, let's say A and B, and the elastic curve is equal to the area under the M over EI diagram between these points. So in your theory one, you are drawing your shear and moment diagram. And then what we're going to use there for deflections and rotation is to divide the moment diagram by your elasticity, modulus of elasticity E, and your moment of inertia I, that is your EI here. So for example, you have this, so for example only that this is your, let's say this is your moment diagram. That is not what we are going to use. We will divide that moment diagram by EI. So if your E and I are constant, okay, if we say E, that is talking about the strength of the type of material. If that is steel, the E is different from the steel of concrete. I mean from the E of concrete. Okay, so E defines the type of material, the strength of the type of material. However, your while your I is with respect to the shape, isn't it? Even if that is both are steel, if the shape of that is I and the shape of the other is square, their strength are different, even if they are the same material. So that is actually in being described by your moment of inertia. This will hold the strength with respect to the shape or the orientation. So for us to determine, since there will be cases wherein your total length of the beam has different types of material, but that is seldom, of course. That is not suggested. However, there will be cases wherein that I is different, wherein let's say the whole beam is not the same size or not the same shape. Let's say, for example, in a case like, let's say this is a simply supported, but later on there will be a cantilever here. Okay, let's say there's a cantilever here. If there is just a less force load that will be handled by that cantilever, you can actually reduce, even especially in your cantilever beams, you can actually reduce the size of the cantilever beam because the bigger the size also, the size will also carry its weight, or the beam will also carry its weight. So the bigger the size, if that is useless, why not make it smaller? So there are some cases wherein your the continue the what do you call this one, the the continuous part of this one, let's say that is a cantilever, is reduced in with respect to size. So again, if the size or shape is different, then I will be different. So it is not always the same. It is not always the case that your moment diagram is the same shape as your uh, M over EI. But again, if E and I are constant, isn't it? Then let's say since you are just dividing the moments, that is originally big, but that will just become smaller, but the shape is the same if your E and I are constant. So again, let's go back to the theorem. So how do you know the slope? If you say slope, that is the angle or the angle or slope or the angle between the tangents. Or let's say I will consider here point A. Let's say that is your point A in your beam, and then another point there, let's say B. Any points, let's say we will consider 2 points. The angle, if I will draw the tangent, this is the elastic curve. If you say elastic curve, that is the shape. If you are going to apply the load, that will now be the corresponding shape of the beam. It will deflect that way. See, because you will not expect that even if your member is very, very strong, there will always be a deflection, even if that is very, very small. And of course that is the case because you cannot see an entire deflection, a big deflection on your members, because that is not elastic. We are using here steel or concrete, but still there is still a deflections or rotations. So let's just exaggerate. So let's say this is your shape once you will apply that load here on top. That is what we call as the elastic curve. Okay, that is the elastic curve. So if you will now consider these 2 points here in your elastic curve and then draw the tangent lines, if they will intersect, okay, the angle between them, let's call it as theta BA, is actually the area between these 2 points in your M over EI diagram. So let's say this is your A, that is your B, this is your MEI diagram. Get the area between A and B, and that is the value of theta, or that is the angle between their tangents in radians. Okay, so that is your first moment area theorem. isn't it? And of course, you discuss about this. So again, that is your first area moment theorem. So this is just a recall again. How about the second? How about the second? Second theorem is that the deviation. That is actually, we are talking here of rotation or the slope or the angle. How about the vertical displacement? That is what we call the deflections. Let's say you want to get the distance of the displacement from the original beam to the deformed beam at A or at B. So that is now your theorem 2. So we are still using your MEI diagram, okay? But how is that? So the deviation perpendicular to the undeformed axis of the member of the tangent drawn from point A from the tangent drawn from point B in the elastic curve is equal to the moments of the area under MEI diagram between these points about B. Okay, I'll explain that one later. But let's go here. If you're getting theta, actually, how do we read that B over A? That is the rotation of B with respect to the tangent drawn at A. That is the meaning of that. Okay, that is that B divided by A. The angle from the tangent of B with respect to the tangent drawn from another point, which is A. Okay, so that is the meaning of that. And if you will go there, continue, that is the symbol of your deflection, delta, or small delta, it could be. So what does this mean? So if you will try to look here at the same points AB and still MEI diagram, the deflection or the vertical displacement between the tangents, okay, we are still talking about the tangents, not directly from the original beam. Later on, you can manipulate using this idea to get the actual deflection of the original beam to the deformed beam. Okay, but for this, since this is just the theorem, so that according to the theorem, if you are going to consider a vertical distance between tangents, this is your theorem 2. Okay, so the vertical, so in your figure here, this vertical distance from this tangent at B to the tangent drawn at A, which is the vertical distance, this is delta BA. Okay, that is the equal to the area between them, moment at 1 with respect to B, since you are getting the vertical distance of the two tangents at the alignment of B. So get the moment of this area with respect to B or about B. So that will give us your uh, delta B over A, or delta, or that is the deflection at B from the tangent drawn from A. So that is the meaning again of B over A. However, let's say you want to get, if you will continue this one, it will intersect, you want to get the vertical distance of point A in the elastic curve to the tangent drawn at B. Okay, your moment arm of this area will be reckoned from A. If you want to get the displacement from A or at A, then you need to moment your area from A. Okay, so that is your moment area method. So using your MEI diagram. So that is moment area method. So later on, if you are using this method, dealing with such cases like this, how do we calculate the areas and how do we moment that one or get the distance, isn't it? Because if you are getting the moment of an area, you need to get the distance of that area into its center or centroid. So you need to know the centroid and areas of different shapes. So these are just for you. Okay, this is from the book of your textbook, which is Kasimali, Aslam Kasimali. Structural analysis by Aslam Kasimali. Okay, so semi-parabola, cubic, this is a third degree equation, parabolic segment, parabolic spandrel, okay, or cubic spandrel, or even if you're talking about higher degree, because again, if you started from an irregular loading, you will end up with an nth degree, a high degree of equation once you will be there on your MEI diagram. Okay, you need to know also. So this is just geometry. Okay, how about conjugate beam? This is also a commonly used method. This is has a similarity with your has something has a similarity with your moment area method because we are using your MEI diagram still. So in this method, okay, this method uses a fictitious beam, which is called the conjugate beam. So fictitious, okay, I will explain that one later. So instead of using the actual beam or the real beam, we will try to construct a fictitious, if you say fictitious, that is for the purpose of analysis only. So we'll try to construct another beam that will represent the real beam for us to analyze the real beam. Okay. So to determine the slope, so that is only for us to determine the slope and deflection at any point on the actual or the real beam. So that is what I'm saying. The conjugate beam is the same length as the actual or the real beam, but loaded with the MEI diagram of the real beam. Okay, so I will explain if we will go on the figure. And supported externally and internally in such a way that its shear and moment diagrams corresponds with the slope and deflection of the real beam, respectively. Given below or in this side is a summary of the equivalent supports to be used in constructing the conjugate beam. So let's go to an example. Okay, so for example here, this is your beam that is originally supported, that's this length, and that is the orientation, originally supported by a hinge and a ruler somewhere there on the length, and that is a cantilever or an overhanging beam. Okay, so the question there is, what is, let's say for example, you want to get a deflection or rotation somewhere there at any points here in your beam. So how do we use your conjugate beam? In your moment area, of course, draw your shear moment and then divide that moment by EI. You will have your MEI. Get the area for you to get the angles or the slopes, and then of course moment the areas for you to get the deflections or vertical displacement. However, in conjugate beam, the good thing in your conjugate beam is that whatever you will be solving from theta, that is always reckoned from your original beam. And whatever you will be solving from the displacement or the deflection is again reckoned already from your original beam. Unlike in your moment area here, that the distances and the angles are not from the actual beam itself or not from the undeformed shape. The theta is from the tangent to tangent. The distance is from tangent to tangent. So you will only have that distance and angle directly from the beam if the tangent at that point is coinciding with the beam. Okay, so that is the disadvantage of your moment area. But in your conjugate beam, that is the advantage because whatever theta or slope we will be solving automatically reckoned from your beam, and whatever delta or deflections that we will be solving automatically reckoned from your beam, original beam or original undeformed shape of the beam. Okay, so how is that? The same we will be using your MEI diagram. So draw your shear, moment, and then divide that one for you to have your MEI diagram. However, we need to construct now your fictitious beam, which is what we call as the conjugate. It says there that in your conjugate beam, we will try to load your MEI diagram. Okay, that is now the load of your fictitious beam. So that is now the load of your conjugate beam. So your ME diagram, we will use that one as the loading in your fictitious beam. And at the same time, as you can see, your supports change because it says there, supported externally and internally in such a way that its shear and moment diagrams correspond with the slope and deflection. So the reason why we are changing the reaction from the real to the fictitious beam is for us to make a way so that the shear of this the shear diagram of this fictitious beam corresponds to the slope of your actual beam, and the moment diagram of that fictitious beam corresponds to the deflection of any point in this real beam. Okay, so how do you change? How will we change? How will we know what is support that we are going to change on the given one? So this is the table given here. Supports for conjugate beams or for your fictitious beam. So if these are your supports for the actual beam or real beam, this will be the equivalent if you will draw your conjugate or your fictitious beam. So just a recall again, if you have external, so these are end supports, simple end. So it could be a hinge or a ruler in your end or your external supports. That will be the same in your conjugate beam. And if you have there a fixed support, of course externally, that will become free on your conjugate beam. If that is original free, that will become fixed in your conjugate beam. And if you have their internal, if you have their reactions in between or interior support, just like hinge and ruler, that will become, a pin and ruler, that will become hinge on the fictitious beam. And if you have their hinge, that will become a ruler on your fictitious beam. Okay, so we will try to, for example, only we have no values for we do not have something to solve. But let's say this is the MEI diagram of that beam and that kind of loadings. Okay, we will try to draw the fictitious beam of that the same length. Okay, let's say the same length, and then the MEI will be used as the loading. So we will now forget, we cannot forget about the original loads. Make use of the MEI as the loading. Okay, however, do not be confused with this. This is the original loadings, okay? And that is the M diagram. This is our M diagram. That is a positive MEI diagram. So it means it is a positive loading. So if you assume that, it depends, by the way, in your assumption, but for you to, okay, simplify this one, let's say always that going up is positive, down is negative, isn't it? So this is a positive moment, ME diagram. So that is a positive. So it means it is a going up. It is trying to concave your beam upward, or that will now try to load it upwards. Okay, a positive, since that is positive. This is a negative ME diagram, so we will load that one as a negative load. So that should be going down. It will try to deflect your beam downwards. Again, it depends. By the way, it depends. But if you will follow this way of loading in your conjugate beam, you will end up with, later on, I will explain what happens in your deflection. Okay, and then we will try to change the supports. Originally, we have an end support of pin, so that will be the same, isn't it? Internal or end support as of ruler or pin, that will be the same. However, we have here an interior support ruler, so according to this, interior ruler will become hinge. So that will become hinge. And then a free end will become fixed, isn't it? A free will become fixed. So this is now your fictitious beam. The same length, but the loading is your MEI, and your supports are changed so that the shear diagram or the V diagram of this type of beam and loading will be the rotation. The theta, that is the rotation or the slope from the undeformed shape, automatically, okay, from the undeformed shape. And then the moment diagram will be the deflection or the delta or the deflection automatically from the undeformed shape. So okay, let's say I will consider here a point x at a distance, a point at a distance x from this hinge, okay, or from this pin. I want to know the rotation at this point from a distance x and the deflection of this point from a distance x. So let's say that is what I want. So now I will construct the MEI. I will load that one and I will create my fictitious beam and draw of course, for you to draw the shear and moment diagram, just like what we did here, okay, what you will be doing on the real beam. Solve the reactions and then of course draw your shear and moment diagram. Now once you have your shear and moment diagram, okay, the shear diagram is equivalent to the theta diagram, isn't it? In such a way that the shear and moment is corresponding to the slope and deflection. So whatever the shear or the shear in your diagram here, that is equivalent exactly to the slope from the real beam. So let's say I will consider this x. So I will get that one and I will get whatever the value in your V diagram. Let's say that is your, I will put there prime so that that will differentiate from your original shear and original moment. So let's say prime will stand for your fictitious beam. So the shear of your fictitious beam at a distance x is equivalent to the rotation on that actual beam at that distance x. Okay, and then the moment diagram, the moment on the moment diagram of the fictitious beam is exactly equal to the delta or the deflection on the real beam or the actual beam. So that is the conjugate beam. And okay, that's the reason why this is the commonly used method of analysis of indeterminate frames or indeterminate structures, because conjugate beams, in the conjugate beam you do not actually need to be establishing this V diagram and M diagram of your fictitious beam. You can actually, if you need that point, all you need to do is get the shear. Cut this one, get the shear. And that is the same as whatever you will be getting in your diagram. Or if you want to get the deflection, use the loading of your MEI and then get the moment at that point. So cut this one, get the moment from left side or right side. That will be the same from what you are getting in your M diagram. Okay, so that is why this is commonly used. Unlike in your moment area, but there are some cases if you are used with your moment area. The good thing also in your moment area, if you have a unknown shapes or unknown curves there, you can always draw the moment diagram separately, isn't it? By parts. We call that one the moment diagram by parts, so that you will just be having triangle, rectangle, or you will just be having their parabolas. And you have the given formulas, isn't it? Here. So what am I saying a while ago is that, okay, see, that is the disadvantage of this, your moment area, because again, once you will have the MEI, yes, you can solve the area, but if that will be combined, a lot of type of curves will be combined, it will be hard for you to find out the centroid of that area. Okay, and again, the most disadvantage of that is that your distances and then angles are reckoned from tangents, not from the original beam. However, if you are used to this, then no problem. Conjugate beam again, that is the way. Okay, you do not need, if you want to construct, why not? Okay, why not construct? But you will expect, even if that is from a point load, it will become, isn't it? That is the succession of your degree. From a point load, it will become a rectangle in your V diagram, isn't it? And if in your M diagram, it will now become an inclined line or a triangle. And then of course MEI, the same shape, triangle, but once you will apply this as load, you will have already a triangular load. So if you will try to draw your V diagram of a triangle, that will now become a parabolic curve or second degree curve. And then draw again the moment from the second degree, it will now become a third degree curves. Okay, it's okay to draw that one, so that all you need to do is use the diagram to get the equivalent values of the shear, or that is the slope, or get the deflection. However, again, that is the good thing in conjugate beam, because you do not need to do that. If you want the shear and or if you want to get the deflection and rotation at this point, all you need to do is cut. Get the shear here by summating forces on this left side or right side, or cut and get the moment, and that is your deflection. Okay, all you need to do only is using your load, get the reaction so that you can cut, consider left side, consider right side. So that is your conjugate beam, and so on and so forth. So let's try. But the good thing here, if you will draw your shear and moment diagram of your conjugate beam, you can actually figure out which part or which at what point on the beam do we have a zero deflection and a zero slope. Okay, so let me show you this one. Last figure. This is our last figure. So let me just copy this theta diagram and delta diagram under your real beam. So I will transfer this to your actual beam, not the fictitious. So as you can see, since we are talking about theta, isn't it? What is theta again? That is the slope from the original beam, or from the, if that is originally horizontal, so slope of the tangent from the horizontal. So if that is 0, if these are 0, so that in this case at this point and that point your theta is 0, that means because if you will try to look at the elastic curve, or that is the deformed shape, that is the deformed shape of your beam. Why is it that your theta here is 0? Because if you will try to draw a tangent there, that is parallel to the original beam, or that is a horizontal. So there is no intersection, so there is no angle, so that is 0. Okay, and in here, why is that 0? Because if that will bend that way and that will bend up, and before it will go down, okay, it will not bend up exactly at this one, because that depends on these forces. So again, why is that 0? Because this is the highest point on the elastic curve. So if I will draw a tangent line, it means that is also parallel to the original beam. Okay, if you will now look at the theta diagram, or delta diagram I mean, is that what are the 0 points here? That is where the support is, isn't it? There will be no deflection because again that is supported. There is no deflection because that is supported. But there is one more point on the beam wherein there is no deflection from the original position. And that is this point. Okay, so that is the good thing. And drawing your theta diagram or V diagram, or your delta diagram or M diagram of your conjugate beam. Okay. So as you can see, this is the deflection. So actually the shape of your delta diagram or your M diagram of conjugate beam is actually the shape of your deformation. Okay, that is the elastic curve, as you can see. Yeah, this is what I'm saying. Okay, so if you consider, so that's why I suggest it that way, because if you will consider this load to be going down, you will change your assumption of positive. The positive M diagram will be loaded downwards and the negative will be loaded upwards. This is the same shape and the same values, but this will be flipped. This will be on top, this will be below, this will be on top, this will be on top, and this will be below. So what do you expect here is that the shape of this is the same, but that is inverted. So you will not expect, you will not follow the actual shape of your delta diagram as the shape of your elastic curve. That is the reverse. If you use the different assumption of the loading. But again, for you not to be confused, that is positive ME. And originally we are assuming that going up is positive and down is negative. So that is should be going down, since that is a positive load. That will become a positive load. And this is going down since that is a negative moment, so we will use that as negative load. Okay, so that is conjugate beam and moment area method. Okay, so if you have any question, then please comment below. Thanks for this wonderful slides. Okay, so that we will be discussing that on the live meetings. Okay, so the next topic we will now be focusing, or we will now be starting on the analysis of these indeterminate beams. So if you have comment or question, you can comment below, or you can ask that one on the live meeting. So thank you very much for watching.